This conference will now be recorded.
So, good evening. Today we are going to start a new chapter, wave optics. So far we had been learning ray optics. So, in the ray optics part, we had discussed reflection, refraction through lenses and mirror, etc., and few instruments we have learned, like telescope, microscope, etc. So, actually, ray optics was based on a model or theory called corpuscular theory. Okay, ray optics was based on corpuscular theory. Okay, so Deepa has also arrived. Very nice, Deepa. We are starting wave optics today. Okay, so ray optics was actually based on corpuscular model. What do you mean by corpuscular model? Actually, according to corpuscular model, light consists of tiny particles called corpuscles. Light consists of tiny particles called corpuscles, and these corpuscles are actually shot with great speed by luminous objects like sun, star, etc., other stars, etc. And with this model, we could explain the phenomenon like reflection, refraction, rectilinear motion, etc. And we have seen we could uh, explain the working principle of lens and then telescope, other instruments, etc. So this corpuscular model actually was proposed by Descartes, scientist Descartes, long back, like long before Sir Isaac Newton. Later on, Sir Isaac Newton had developed this corpuscular model or ray optics by his own, and see, according to corpuscular model, light is consisting of tiny particles. And before this corpuscular model, Sir Isaac Newton was known for his classical mechanics. He is the father of classical mechanics, and he had given the laws of motion, where he had taken all the object or consider all the object as a tiny particle. Okay, and particle is actually particle is characterized by position and momentum. Okay, so see, if you just remember laws of motion or your classical mechanics lesson from the 11th standard, the simplest motion is actually linear or one dimensional motion. Okay, where particle moves in a straight line. So kind of this idea, since Sir Isaac Newton had this idea that tiny particle may move in a straight line as seen in classical mechanics. Similar to that, if light is consisting of tiny particles, then light must travel in a straight line because each particle will travel in a straight line. Okay, and see, with that model, it was able to like he was able to explain all this phenomena. So it was very nice so far. Okay. So what was the problem, or where was the limitations of this ray optics or corpuscular model that we had to propose another model of optics, that is wave optics. And you will see in higher classes there is quantum optics also. So whenever we propose further and further developed or modern theory, there must be some limitations in the older theories. What were those? Let us see. So why wave optics? See, in the ray optics, we have seen that light travels in a straight line. Okay, it doesn't get bent while traveling from one place to another unless there is an obstacle. Even if there is an obstacle, then the light is stopped. This there will be shadow over here. Okay, shadow, dark. Okay, if suppose see here, it is seen experimentally that light actually gets bent at the sharp edge. Look, if you have a cardboard and make a big hole and you put a light over here, see, light actually should go straight line so that we get light at like in between this region, and rest of the places there should be shadow like this. Okay, rest of the places there should be shadow. But it is seen that if your like if the hole is made very narrow, okay, very narrow hole in the cardboard, it is seen that light is diverging. Okay, it is bending and it is reaching to the geometrical shadow region. Actually this should be, according to ray optics, this should be shadow, but there is some light. Okay, this should be shadow region, but you see the light is actually entering into that shadow region, and there will be some dark and bright pattern. Okay, so this is the natural phenomena, like one of the natural phenomena which was which ray optics was not able to explain. And this is called, this bending of light at the sharp edge is called diffraction of light. So diffraction of light was one of the phenomena, natural phenomena, which ray optics could not ray optics could not explain. Okay, so there here is the limitation. Not only this, we'll show you few more limitations of ray optics. See, if there are two lights, okay, obviously we'll say, like we'll see two coherent light, when they superpose, they produce alternatively, see, this is bright, this is dark. Okay, bright, dark, like this. See, this is dark region, this is dark region, this is a bright dark, bright dark, like this kind of bright and dark bands. Okay, see, it is really a fact of, like fact to be surprised, that how come two lights can produce a darkness. See, bright regions are fine. What we expect, if you have two light like superposed together, okay, you should get more brightness rather than getting darkness, right? So it is really a surprising thing that when two light, obviously we'll see, not all cases, coherent light wave, like coherent light, when they superpose or upon combination, create this alternating bright and dark patterns or bands. This is called interference of light. Interference of light. So this was another phenomenon which was not explained In fact, it was like ray optics was not capable of explaining this phenomenon also. Okay, another phenomenon called polarization, in which light ray will be confined to a particular plane, vibrating, or it will be confined to a particular plane, that is called polarization of light. So these are mainly three phenomena so which were not explained by ray optics, or ray optics could not explain these phenomena. So polarization of light, so diffraction, interference, and polarization of light. Okay, so I'll just name here. So interference, let me give the first name, interference. Okay, then diffraction, bending of light, diffraction. Then third is the polarization of light. So these three, mainly these three phenomena of nature, ray optics could not, ray optics could not explain. Okay, or I can say corpuscular model could not explain these three phenomena. So then, Dutch physicist, Dutch physicist Christian Huygens proposed that we can explain those phenomena if we consider the light as wave, and in fact, light travels in the form of longitudinal wave. He proposed this. Okay, longitudinal wave. But obviously, light is not longitudinal wave. We know it is transverse in nature now. Okay, light is electromagnetic wave. We know now. But during that time, it was not accepted because light. See, the only wave that time was known is the sound wave. During this reign or this time, when Huygens proposed that light could be considered as longitudinal wave, but light was not requiring any medium, but the only wave was known during that time is the sound wave, which requires medium. So his idea was in doubt and people did not accept. And also there is another reason, because the greatest scientist Sir Isaac Newton did not agree with this wave model. But later on, when Fresnel and Young, they they had observed various experimental facts, and those could be explained with this wave nature of light. But that time another problem was that they thought that, like Huygens thought that light may be traveling through an all-pervading hypothetical medium called ether. However, so slowly wave theory was getting some importance, and later on in 19th century, when Maxwell, I'm sorry, I think yes, 19th century, when electromagnetic theory was developed by Maxwell, and there he proved that light can travel in vacuum. Okay, in fact, he actually found out the velocity of light in vacuum, that is 1 by mu 0 epsilon 0, that we have learned in electromagnetic wave chapter. Okay, he could actually resolve these two problems, that and light is electromagnetic in nature and transverse in nature. It is composed of okay, yeah, so it is the electromagnetic wave. And see, Michelson Morley experiment, they disproved the existence of ether. So these are the informations you should remember, like how the wave theory was accepted. So, what we have discussed, what was the earlier concept in ray optics? So they considered light as consisting of corpuscles. Corpuscles are traveling in straight line, and they are shot with great speed by luminous object, and light can travel in a straight line. So these are actually contradicting to the phenomena I have discussed now: interference, diffraction, and polarization. Those are not those we could not explain with this corpuscular model. So this wave theory of light could successfully explain the phenomena. Like Fresnel's Young, they had actually executed many experiments on this, and those phenomena were actually, we'll see Fresnel's diffraction and Fraunhofer diffraction. So in this chapter, what we are going to learn is, like, first we'll learn Huygens principle, and then we are going to learn interference, diffraction, and polarization is also there. Recently the syllabus has been reduced, polarization has been removed from the syllabus, but we'll discuss for competitive exam. Okay, so look, our today's topic will be wavefront. So far we had an introduction. Now we'll go to the actual topic, that is wavefront, ray, and Huygens principle. And using Huygens principle, how we can prove. See, whenever there is a better theory that must explain the phenomena which were explained by the older theory. So reflection, refraction, those were explained previously by ray optics. Now you have to prove your wave theory to be superior. You have to actually prove the laws of reflection and refraction using wave theory. So that was done by Huygens. We'll just learn today. So let us first learn step by step few basic things we'll learn first. So we'll learn a term called wavefront over here. Whenever we are going to learn or discuss wave optics, we'll be using this word or this term wavefront. So what is wavefront? Before I go to the definition, let me show you this figure. See, this figure shows that whenever you just drop a pebble or a stone, small piece of stone, on the calm and quiet water, okay, in the tank or maybe in the pond somewhere, then what you look is that there are some circular patterns which are actually traveling from the point of impact. They have created at the point of impact, and these circular patterns, somewhere it is having little like height, somewhere it is actually uh, the water particles gone down, somewhere water particles are going up, like this. So they are going like this, so somewhere up down, like that. So this is called disturbance or wave created at this point of impact, and this wave is actually traveling in terms of or in the shape of circular patterns. Okay, and look this figure, the same thing here, it is little bit magnified. And look here, this is called trough and this is called crest. If I say in terms of wave, you have learnt in the sound wave, when the particles are having maximum vibration, okay, or displacement, that is called that is called crest, and trough is the this part. Okay, anyway, so we know these things. Like, sorry, this is trough. Okay, this is the one. Okay, anyway, so you can see, if I just take one such circle, as you see circular patterns, if I take one such circle, see, every particle on this circle or circumference of the circle, every particle, they are actually moving upwards at the same time. they are moving at the same time in a similar manner. And if I take this trough here also, the particles of the water is actually vibrating or going down, vibrating downwards, all particles vibrating downwards together in this trough also. So what I mean to say is the particle vibrating with, see, together, the particles which are vibrating together, those are on this circumference. Similarly, if I draw a circle over here also, you will find that all the particles on the circumference of this circle, they are also moving or vibrating together. So the particles which are vibrating together with at the same time in a similar manner with a similar amplitude, they are called they are actually said to be in phase. In phase. Okay, they are in phase. In fact, here also all the particles will be in phase. So whatever circular patterns you see, whether it is crest or trough, so particles either in the crest or in the trough, they are vibrating in phase. But don't think that the particles on the trough and like trough and crest, they are also in phase. They are out of phase because these particles are moving upward, these particles are moving downward. See, they are going downward. Okay, so you can see this portion is trough. I'm saying the water particle are moving like vibrating into the into the plane of the water surface, and they are coming outward. See on these circles. Okay, so what I mean to say is that these here all the particles which are vibrating together are called are said to be in phase. Okay, so if I take all such particle and draw a line, okay, or a surface, then that line or surface is called the wavefront. So here is the formal definition. A wavefront is defined as the continuous locus of particles of the medium which vi- which vibrate in the same phase at any instant. Okay, at any instant, all the particles are vibrating in phase. So this is a circular pattern. This circular pattern is called wavefront. This is called wavefront. Circular patterns are called wavefront because I am just drawing. Okay, I'm connecting all the particles with a line here in a circle. So the locus of all such points which are vibrating in phase is called wavefront. Okay, so this definition is very important. You have to know what is wavefront. And wavefront is a surface of constant phase. So if you take this whole circle, okay, or if it is a spherical kind of spherical, then you have a surface of this radius. Suppose this radius r1. So everywhere on this surface of radius r1 will be in phase. So that's why this is called wavefront is actually constant phase surface. A surface with constant phase or surface of constant phase. And see the speed with which the wave fronts, see these wave fronts are created at the point of impact, but they are not just sitting. They are actually moving or spreading out. As you can see, spreading out. You might have this experience practically also. So these wave fronts are propagating with the velocity of light or speed of light in that particular medium. If this is water, okay, this is the water wave. So these wave fronts will be actually moving with the speed what water waves would actually propagate. Okay, so this is actually about wave front. Now if you draw perpendicular to this wave front, okay, then you look this perpendicular. This is another perpendicular. Actually, these are called ray. Okay, straight perpendicular line, perpendicular to the surface, obviously perpendicular to the wavefront or the surface. They are called actually ray of light. Okay, suppose you have been given a plane wavefront, then what will be the ray? You have to draw a draw the perpendicular. Okay, then you get ray. Okay, so anyway, I have shown you here circular or spherical kind of wavefront, but the geometrical shape of the wavefront differs, and that depends on the source. Here in this case, you have just impacted a point over here in the water surface, so you get circular or kind of spherical wavefront. So depending on the source, nature of the source, you get different shape and size of wavefront. If you have a point source of light, then you get spherical, because see, after producing wavefront from here, the wavefront will be actually spreading out in all direction symmetrically, so it will give you spherical surfaces. Okay, so point source of light will produce spherical surfaces which will be spreading over all over the space. So this kind of wavefront is actually called spherical wavefront. So this is spherical wavefront, as you can see here. So the source is actually point source. Now look, if your source is not a point source, it is a line. I'll show you how line source is. See, this kind of line source in the sodium vapor lamp in your laboratory you will get. This is a line source. If your source is line, that means, see, you can get light rays from here. If your source is line source, then the wavefront you get is actually a cylindrical wavefront you get. This is the cylindrical wavefront, and in this case also, look, the waves are actually getting distributed all over the circumference of the cylinder, and the shape will be cylindrical. Okay, so this is called cylindrical wavefront. Now we have got spherical wavefront, we have got cylindrical wavefront. Now look, if these wavefronts, like suppose my point source of light is at very far away, then see, from very far away we can see a part of the spherical surface. We see a part of the spherical surface like this. So that's why when we see a point source from very far, we'll see wavefronts will be plane wavefronts. Okay, even for this also, if you have a line source like our tube lights, okay, if we are nearby, then the wavefronts will be cylindrical. But if we see from very far, it will be actually plane wavefronts. Okay, so you'll get kind of these surfaces. Okay, plane wavefronts. So these are different types. As you, so here point source, here is actually a line source of light, linear source of light. And here actually at far distance from spherical or cylindrical wavefront. Wavefront, I'm just writing like this, wavefront. So at far distance from spherical or cylindrical wavefront, they look like plane wavefront. Okay, they will be looking like, okay, they will look like plane wavefront. Okay, so these are the thing. So okay, so we have learned what is wavefront. Okay, now we'll go to Huygens principle. Okay, so So Deepa, is it all right? Is it clear to you so far whatever we have discussed? If not, you can ask me in between. What is wavefront? Do you understand what is wavefront? It is locus of the points of the medium through which the light, through which a wave. Actually, this is not for only light. This is for anything. Okay, through which the wave propagates. Okay. All right. So let us see the Huygens principle. According to Huygens principle, each particle on a wavefront act, acts as a secondary, like source of secondary waves. Okay, I'll explain what it is. Which add up to give wavefront. Like see, if I have a if I have a plane wavefront, look, I have infinite number of points in this plane. Okay, large number of points. So each point will act as a source of secondary waves. So if I take plane wave, actually to denote plane wave, we will be taking a straight line. To denote a spherical wavefront, we will just take a sphere. Okay, so suppose this is a plane wave. Okay, so each point on this, according to Huygens principle, each point on this wavefront, if suppose this is A and B, on this wavefront, each particle on this wavefront or each point on the wavefront will act as source of secondary waves. That means what? They will also produce. So point object means what? They will produce mostly in the nearby spherical, spherical waveforms they will produce. If I take this is another point, so there this also will create like this. If I take this is another point, this also will take like this. Okay. So all the points on the wavefront will act as source of new wavefronts or secondary wavefronts. So those wavefronts are called secondary wavelets. Okay, and the new wavefront later at any time can be given by the forward envelope of secondary wavelets at any particular point. So if you want to find out the position and shape of the new wavefront produced by each point of the on the each point on the wavefront, okay, or each secondary sources. So where will be the position and what will the shape of that wavefront after particular point. So that is what was given by Huygens, okay, Huygens, and these were the assumptions as you can see. So what was the assumption? That each point on the wavefront will act as secondary source, and the secondary waves which are produced are called wavelets, secondary wavelets. Okay, and the secondary wavelets spreads out in all direction with speed of light in the given medium. Now look, we'll just see Huygens construction. Huygens construction to get. So what is this Huygens construction? It is actually geometrical method of locating the new position and the shape of a wavefront at any instant from its known position and shape at any other instant. That means suppose you have a source of light. Here I am showing you. Look, see, suppose I have a source of light over here. So we know at any time, suppose at any time, the wave front is here because it is producing wave front like this. See, this is dotted line is the wave front, and this is actually I can draw some other also. So they are actually spreading out like F2, G2, these are also wavefronts created by this O. They're spreading out. So at any instant of time, if you take a still picture, this you will see. All the things we will see. Anyway, what I am doing here, suppose I am thinking that at any instant of time, you have the wavefront here at this point. Okay, F1 and F2. This is the wavefront I have at any instant of time. Okay, at any instant. Okay. Now look, according to Huygens principle, we know each point will act as source of secondary wavelets, isn't it? And here I'll just consider that the wave produced here will be spreading out with the speed v, and I'm thinking that after any time t, I just want to see at after any time tau, I want to see where will be the position of the wavefront and what will be the shape. Look, each point you look here, there are some representative points given. Representative points are a, a, and here maybe some other points. Okay, so these are actually representative points. Look, these are the representative points on the wavefront F1, F2, and each of them will act as secondary, like source of secondary waves. And see, I'm just trying to locate after time, after tau time later. Okay, after tau time, I just want to locate it. So what you have to do, you have to see, since point object or point source will create a spherical wave, sorry, spherical wavefront. So you look here around this, like making this A as center, there is a sphere here. Look, this is a sphere. Okay, it is shown half. So the wavefront it creates, it will actually travel with the speed of the wave itself. So this is v, and suppose after time tau I am seeing, so what will be the distance, linear distance from a to a prime? This will be actually v tau. Okay, this will be v tau. So this is the radius, or this is the distance. So with this radius vt, I am just drawing a circle which actually touches the, okay, I'm just actually in the beginning, this will not be there. Okay, so in fact, see, first I was thinking like this. You have this first. Okay, then I'm just locating points. They will create wavefront, spherical wavefront. But what will be the radius? V into t. So look, this is v into t. Okay, this distance is v into t. I am taking some other points also. So this is vt. This is also vt. Now look, if I draw a common tangent to all these three, then I get the new shape and new position of the wavefront. Okay, so this is what has been done over here also. Look here. So this is the f1, f2 is the beginning at, like, initially. I'll write initially. Initially, this is the position. Now each point acts as a secondary, like source of secondary wave. So I'll just, to construct the new wavefront, I have to draw a circle, because each point sources will be creating circular patterns or wavefront of circular patterns. So this will actually reach here. Okay, so the sphere I'm drawing, this is actually having radius v tau, because speed, with the speed of light v, the wavefront is moving in the forward direction, and tau is the time. So during this time, this is the distance it can travel. So this is the radius of the sphere, circle or sphere we have drawn here, sphere. Okay, so similarly with all the other points, if I draw like this point, if we draw and take a common tangent, suppose I have surface like this, I have surface like this, so they may have common tangent like this. So if I just draw a common tangent to this, like this, spheres, common tangent to these three spheres. This will look like actually the line if we connect to them. So we can see that G1, G2 will be the position of the new wavefront. Okay, position of the new wavefront. Okay. Now let us see with the plane wavefront. See, this is f1, f2 is the plane wavefront at t is equal to 0. I want to see what is the size, what is the shape, and what is the position of the wavefront, plane wavefront at after time tau. So look, as we see, if you want to construct, you have to consider some points on the source itself. Then each source, sorry, on the wavefront itself, and each wavefront, sorry, will each source will produce spherical wavefront of this v into tau if the velocity is v, so v into tau, and these pairs actually will uh, see they are having radius of v tau because v is the speed of the wave I have taken. Now if I have, see, this these blue lines, they were in the beginning, because see this will be kind of pattern like this. Now if you draw a common tangent to all this, look, you get like this. So this is G1 and G2. This is the forward envelope it is called, and also it is called the common tangent at later time tau. So so this is how, by Huygens construction or geometrical method of construction, can give you the position and shape of the wavefront, new wavefront, if you know what was it earlier. If you know the shape and size, or what was that in like earlier, if you know the position and the shape, and at later time, any later time tau, you can find out the shape and size. Okay, so this is actually Huygens construction. Now quickly what we'll do, we'll use this Huygens principle to prove the laws of refraction and laws of reflection. Look here, this law of refraction, you know the Snell's law. We have to prove the Snell's law. So to do that, okay, let me write the Snell's law, n1 sine theta 1. This is in the first medium, suppose, and n2 sine theta 2. Okay, theta okay, theta, instead of theta I'm writing incident, angle of incidence I, n1 I, and n2 r. That will be better, n2 sine r. So r for reflection, I for incidence. So look, to do that, what we'll do, we will be using Huygens principle to do that. What we have taken, we have taken two medium, the two transparent medium. Suppose we are seeing, like we are just observing this experiment. So this is one medium having, so this is medium 1 having velocity of light in this medium v1. Okay, so you can find out what is the refractive index. So in this case it is given. So other one is medium 2. This is actually given as, this is actually a denser medium, suppose denser medium, and medium 2 has velocity v2, which is less than v1. We'll prove that why it is so. And look what we are doing here. This p prime is the interface. So refraction happens at the interface of two transparent medium like air, glass, air, water, air, spirit, etc. So this is the interface. Okay. Now I'm taking a wavefront AB. I'm taking a wavefront AB. See, AB wavefront, which is actually traveling from this side. Okay, AB. And as I said, if you have wavefront like this, if you draw perpendicular, it will give you the direction of propagation of the wave. Okay, so this AB is the plane wavefront. Suppose plane wavefront as it is seen, incident, plane incident wavefront. plane incident wavefront. Okay, and the wavefront is actually getting incident at an angle I with the interface. As you can see, PP prime is the interface. Now see, the B point is here for the AB wavefront, AB plane wavefront, AB plane wavefront, wavefront. It is getting incident at this particular interface at I angle. Now look, if I want to calculate, sorry, want to find out or find the shape and size of the new wavefront produced, then what I need to do is you need to draw a sphere, as you can see from this A. Okay, this is the sphere, the part of the sphere. So look, I'm thinking that the light wave or wavefront actually traveling this point and touching this. See, if it is refraction means light travels through the medium. Okay, so medium goes from one medium to another medium. That means this B has to come up to C. Suppose the velocity in the first medium is v1 and tau is the time this wavefront or the waves which is produced by wavefront produced by B is reaching to C in tau time. So what will be the distance of BC? This will be v1 into tau. I'll just repeat it. See, this is the BC length. This length is equal to v1 tau because the v1 is the velocity of the light in the medium 1 and tau is the time it takes a light or a wavefront takes to reach from B to C. So this is the BC length. Now look, if I have to construct the new place or new position and shape of the wavefront, I have to draw a sphere taking this AE as radius. What I'm thinking? I'm thinking that in tau time, the wavefront produced by this point A, as you know, each point on the wavefront will produce secondary wave. So secondary wave is produced by this point A, and in this time tau, it is moving up to E. Okay, so thinking that I'm just drawing a circle. Okay, circle right actually like this, or a sphere. I can say sphere. You're drawing a sphere with the radius v2 into tau. Why? Because this much distance it can travel in time tau. So look, it can so we can write AE is equal to V2 into tau. Okay, AE is equal to this. Now, if I compare this to, okay, so look, I said you have to draw the spheres and then you have to take common tangent. Common tangent, as I was showing, if you have a plane wavefront, you have many points on it, so they will create spherical wavefront like this. So you have to take the common tangent on all of them. So here it is done, similar thing. So look here, this is BC, this is AE. Look here, this there is a tangent drawn from C point on this particular circular arc or spherical arc. So this is the, suppose this is point E. So now I can think that the position of this new wavefront will be here. When? After time tau. After tau, T is equal to tau, the position of the new wavefront will be where? EC. EC will be the new wavefront, plane wavefront. Okay, EC will be the new wavefront. I hope you have understood. If not, please read the textbook. You will understand again. Or if still there is some problem, you can ask me. So the plane wave is getting incident at this point, making an angle I, and see what I'm thinking. After time tau, I want to see the shape and position of the wavefront. So to do that, I'm thinking that the BC point on this wavefront, plane wavefront, takes time tau to come up to here. C. So what is the distance is travel? V1 into tau. This BC is in V1 into tau. See, in the medium 2, the light has velocity v2. So if suppose this A point is creating an wavefront, that will travel up to AE, which is equal to V2 into tau. Okay, V2 into tau, and I'm I'm drawing a sphere with this radius V2 into tau. Now what you have to take? You have to take common tangent. So you just draw a tangent from C to E, okay, on this sphere or spherical surface, and that's how you get EC as the plane wave. So EC is the new wavefront. EC, this new wavefront is EC. This is the new wavefront. Okay. Now what we'll do? We'll just do the calculation and show you how Snell's law is valid here. See, I have two triangles. I can take A, B, C triangle, and what else? A, E, C triangle. See, for A, B, C triangle, if I just write sine I, so look, this is the perpendicular. So BC is the perpendicular. So perpendicular by hypotenuse. Perpendicular is BC, by hypotenuse is actually your AC. Similarly, for sine R means I'm just taking AEC triangle. Okay, so this triangle sine R means perpendicular is again AE by this AC. So if I just take the ratio sine I by sine R, what I, what we get is BC by AE. Okay, BC by AE. Now look, BC means what? BC means this one, this distance, this is V1 tau, and AE means V2 tau. So tau goes off. So what you get is sine I by sine R is equal to V1 by V2. Now look, what was written? V2 is greater than, sorry, V2 is less than V1. This I have to prove. Let me uh, tell you one thing here. If you want to find out the Snell's law, n1 sin theta 1 is equal to n2 sin theta 2, then you can just find out refractive index means what? N1 is equal to C by V1 and N2 is equal to C by V2. So if you just put the value of V1 is equal to C by N1, okay, and V2 is equal to C by N2. Okay, so you get V1 means, so N2 by N1 you get actually. Okay, so N2 by N1 you get. Now if you just multiply, see N1 sine I1, sorry I, and N2 sine R. N2 is the refractive index of the medium 2, N1 is the refractive index of the medium 1. Okay, so this is how we can prove the laws of refraction from Huygens principle. Okay, so I'll just take another just 5 minutes to prove the law of reflection using Huygen's principle, then I'll stop the class. See, so here there are few more things, like if you just consider this as the wavelength lambda 1 here, then obviously this will be lambda 2 in the medium 2. So you can see, if you write directly BC by AE, that means lambda y, see sin I by sin R, it will be lambda 1 by lambda 2. And you know this lambda 2 is obviously small, so you can see that lambda 1 is greater than lambda 2. And in that case, so V1 is greater than V2. So this is also proved here. And one thing you have to remember, that the frequency of light doesn't change upon refraction. The frequency doesn't change, does not change upon refraction or reflection. Refraction or reflection. Okay. All right. So we'll just prove the reflection part. See, I have taken here again AB plane wave, and you know this is the plane mirror. Mn is the plane mirror. Mn mirror. This is the plane mirror, and you have wavefront AV, initial plane wavefront, plane wavefront initially. Okay. Now what happens at certain instant of time t equals to 0? Suppose it just incidence on at this point A already incident. Okay. And what is the angle of incidence I here? And see, uh, to construct the reflected, so this is actually initial or incident wavefront. This is incident wavefront. Okay, this is already denoted. And the reflected wavefront is this. If you want to construct how to construct the reflected wavefront, is that you have to think like, see the point over here. Suppose it takes time to tau to reach for the wavefront which is produced by this B point to reach up to C. So the time taken by wavefront to reach from B to C is tau, suppose. Okay, tau. Now see, the light actually are always in the light rays are always in the, or the wavefront is always in the, everything is happening in the same medium. So the time it takes to reach to C, obviously if this A point is producing an wavefront, that particular wavefront will reach up to E here, suppose during this time tau. Okay. Now what happens? So BC is V1 into tau, and what about AE? AE also will be equal to V1 into tau. Okay, I hope you understood this, because BC takes time tau to reach up to C. By that time, the secondary wave front produced by A will travel up to E. Okay, so that's why this is the thing. V1, both are equal. Now, if you want to construct this reflected wave front, you have to actually draw a sphere of radius V1 into tau. Okay, this AE, look this AE as radius. You have to draw a sphere like this. Okay, and you have to draw a tangent from C onto this sphere. From C to this sphere, you have to draw a tangent, and then that tangent will give you the position of the plane wave front. So EC here, this is actually new wave front, EC. Okay, EC is the new wave front, WF for wave front. Now you have to prove that angle of incidence and angle of reflection must be same. Okay, so this can be proved actually. Look, these are actually, see, this angle is 90 degree. This AE, okay, AE, AE and C. I'm taking two triangles AEC and ABC. These two triangles are actually congruent triangles. Then I can prove I is equal to R. So this is how you can prove the law of reflection by the use of principle of Huygens, okay, or Huygens principle. So this is how you have to uh, like prove the laws of reflection and refraction by using Huygens principle. So you can see that wave theory can explain the laws of reflection and refraction very well. Okay, so with this I'll just conclude this lecture for today, and next day we'll take interference of light. Okay, so Deepa, do you have any doubt so far?
No, sir.
Okay, thank you very much. So I'll just conclude this lecture here. We'll meet again on I think Wednesday for the same wave optics. With the same wave optics, I'll come up with interference there. Okay, see you on Wednesday. Bye. Bye for today.